Okay, so I just want to welcome everybody. Thank you so much for taking some time to spend with us in this Big Issues seminar series. Some of you have heard a lot about this over time, and some of you, this may be your first blush with this opportunity. So what I want to do is talk just a minute about why we're here and what we hope to do with our speaker today and tomorrow, as well as in the future with some of our speakers that we're inviting. Thanks so much for coming. Really appreciate everybody's time. I know that everybody's busy, so I'm glad that you're here. One of the things that we wanted to do as a faculty is to start putting ourselves in the place of where we're going in the future. So we created this Big Issues seminar series because we want to get out of our normal kind of teaching, extension, and research programming, daily programming, and be ready to address some of these daunting issues that we're facing in the country, which increasingly are impacting crop production and distribution in our normal systems, as well as how our systems interact with consumers. So our idea was to invite well-known, well-respected speakers who are forward-thinking to come to campus and launch us into a process of actionable reflection and really spark this cross-disciplinary dialogue. And so we're happy to do that with the first sort of inaugural version of this. We ask speakers to come and challenge our views, present us with identifiable opportunities, and really help jumpstart both developing tools and applications for resilient systems, and also to help us prepare future leaders to navigate this fast-changing world. So that's what we're hoping to come away with today. For big issues, we identified, pinpointed several big issues that we wanted to focus on to get us ready. The first one was fossil fuels and renewable resources. We'll talk more about that, especially as it relates to the generation of power. The next one will be climate change and the carbon economy. And then we're going to follow that up with another speaker talking about diet and driving the health crisis in the country and how we might respond to that. So let's talk about why we're here in terms of fossil fuels and electric power. That's the first big issue that we're tackling. And really it's because energy underpins everything that we do. It's the fundamental connector that underpins how the country's agriculture interfaces with consumers. We want to know how to adapt our systems on scale and at pace that's never been attempted before. We hear about this many times when we're talking about renewables, but renewables-based electricity differs from fossil fuels far more than fossil fuels use differs from each other. And so we're really hopeful to hear some of that in Dr. Michaux's talk. Speaking of Dr. Michaux, why did we invite Simon here today? So we invited Simon because his talk about this transition challenges and coping with them is really perfectly fit as a very well-known speaker, respected and forward-thinking. And I think after today, you'll realize that he's also a first-class communicator. We wanted him to come and bring his intellectual background, his understanding, and his wide experience with the industry, the government, and university sectors. So he's been around the world. He can tell you the mileage just this month alone that he's concocted for travel and giving talks like this. And so we're happy to have him. Simon's an associate professor of geometallurgy at the Geological Survey of Finland, GTK, which you see on the slide behind me, in the Circular Economy Solutions Unit. He holds a bachelor's degree in applied science and physics in geology and a PhD in mining engineering from the University of Queensland in Australia. After his PhD, Dr. Michaux worked for 18 years in the Australian mining industry in research and development, and then for a year at the multinational engineering firm Ausenco, and for 3 years in Belgium at the University of Liège, researching the circular economy and industrial recycling. He then moved to GTK in Finland, first to work in the Minerals Intelligence Unit before joining the Circular Economy Solutions Unit. Besides these accomplishments, Dr. Michaux stands out as a highly credentialed source of information and ideas, which are widely distributed in the literature, YouTube, and other social media outlets. His many lectures and podcasts have gained international attention and stimulated lively debate online. In the social media space, he sets a fine example in both responding to critics who descend to ad hominem arguments instead of engaging in data and ideas. For most of us, he is a scientist who, like most of us, he's a scientist who takes a long and ultimately hopeful view of the future. So, Simon, I'd like to thank you for coming and introduce the first talk in this 2-seminar series, Industrial Transformation Away from Fossil Fuels will not go as planned. And direct you also to tomorrow's talk at the Rights Union at 10:30, where we'll talk a little bit more about what the future looks like. Thank you.
Okay, thanks. Sound okay? Yeah. All right, guys, let's crack on. So I'm going to give you a summary, a lightning fast summary of the work done over the last couple of years. Industrial transformation away from fossil fuels will not go as planned. Why do I think that? Why was this work done? Well, excuse me. When I first came to Europe from the Australian mining industry, 2015, I was expecting that Europe was actually leading the world in transferring away from fossil fuels. And what I was expecting was a plan, a feasibility study-like plan to industrial reform. What I wanted to see, number of power stations, where they will be, what kind will they be, who will own them, who will operate them, what infrastructure will go between them. It's not rocket science, guys. Why is this so hard? What I found was there was no plan. And in fact, the more I looked, there were no numbers. The entire thing was arm waving. And this terrified me because the mining industry had just crashed and people who were doing good work were out of a job. Whole companies were going down. So for the last 7 years, I've been trying to actually understand how could I communicate what I was seeing in a form that couldn't be ignored. What was also apparent was there was no discussion at all about our dependency on fossil fuels. We're going to replace fossil fuels, great, but we need to understand what we're replacing. There was even less discussion about our dependency on minerals. Europe doesn't mine raw materials. We buy things from the market. The extraction of raw materials is someone else's problem. Now, from the mining industry, I'm here to tell you that we do indeed consume minerals on a day-to-day basis. It was a blind spot. So the whole commodity sector had been misunderstood. It was seen as a market action. Throw money at it, you'll be right, new resources will magically appear. They weren't seen as a series of finite resources with engineering bottlenecks and extraction. So assumptions and promises were being made, which clearly were not going to work in mining, refining, smelting, and manufacturing. It just wasn't there. So I did some very simple calculations, and I sat my management down in Finland, and this was 2018, sorry. And I pointed out that at some point, the captains of industry in Europe, which believed they were going to take over the world in terms of electric vehicle and battery production, and they were going to turn to the geological surveys of Europe, GDK in particular, because we manage a battery minerals portfolio. They were going to ask this question: why did you not tell us about this really bleedingly obvious problem? And once management understood that, they go, yeah, okay, you better get in front of this. Right. So when we're talking about global strategic transformation, we often talk about carbon emissions or climate change. Okay, great. But the how? There's no discussion about the dwindling resources that we wish to replace or the finite natural resources we're going to replace them with. Why is this so hard? So the green transition will happen. Fossil fuels are going. The technology we will use is what I will discuss today: wind turbines, solar panels, electric vehicles, hydrogen fuel cells. We will use these things. But my point is it just won't go to plan, not the way we think. So before I get to there, I'm going to show some other information in a parallel piece of work to show this is not a tickling competition. This is not a theoretical thing that might happen 50 years in the future. It's happening now, and it will happen on our watch. So we are required to switch our brain off. Sorry, switch it on. We're required to switch our brain on. There's that jet lag, sorry about that. Yeah. All right, what I've done here is I have overlaid the metal prices of everything the World Bank uses to track the industrial health of the system. So what I've done here is overlaid each of the curves and indexed them to the number 100 and the month December 2001, and the data goes back to 1960. So what I'm showing here is periods of stability, relative stability. So apart from the 1979 oil embargo, it's been pretty stable. But in January 2005, that happened. Ouch. I make the case that this actually related to a chain reaction in the oil industry. So that's the point where the US dollar decouples from the gold standard. That's the 1979 oil embargo. The GFC, global financial crisis. So what I'm saying here is the global financial crisis was actually caused by a blowout in metal prices 3 years earlier, which was in turn was caused by a problem in the oil industry. More on that later. So the largest economic correction we've seen in some time was not enough to change the volatility, and the problems are still there. And then that brings us to, well, we fixed it with quantitative easing and all the problems went away apparently. And then we got to COVID-19, the gift that just keeps on giving. We've had another blowout. So a case can be made that this blowout was a chain reaction that started in the oil industry. A major economic correction made absolutely no difference at all, so the problems are still there. And the change happened 18 years ago. So this is not something that might happen in 50 years. It's happening now. We're decades into it. So what happened? Oil plateaued. January 2005. Oil supply was not able to expand and plateaued, yet demand continued to increase. The Saudi Arabians were the swing producers of the day. They were told to increase production. Well, I don't know if they were told, but that's their job, to increase production. What was apparent was their production actually declined while they had a 146% increase in rig count in exchange for a 4% decrease. They had actually overstretched their asset, and now they're sweating that asset as fast as they can. And that's the same point. The Saudis could not increase oil production plateaued. So the chart on the left, the green is conventional oil, the yellow is Canadian tar sands, and the red was the fracking industry as it was at the time. There was an evolution in horizontal drilling which allowed fracking to take over later. But at the time, that's all we could do. And that caused the blowout. So this is oil price, supply and demand up the top, and then we've got oil price down the bottom. So oil production did plateau for a short period of time, and within that plateau, oil and supply and demand did separate, and that translated into an oil price spike. And that oil price spike, the price of oil peak, was the temporal marker for the start of the global financial crisis. Oil is at the center and the heartbeat of the whole industrial economy. More on that later. And we fixed it with quantitative easing. And then fracking in tight oil takes off, and evolution in horizontal drilling, and that saved the day. So the GFC was caused by a chain reaction that had its genesis in the oil industry and could be seen in a blowout in metal prices. The GFC is when the weakest link broke, which has happened to be in the real estate industry. But that wasn't the cause. That was just the weakest link that broke. And we still haven't fixed it, and those problems are still out there, and we are mostly unaware of what that actually happened. Does that mean we are vulnerable for it happening again? Yes. Right, so fracking or tight oil was able to make up shortfalls. The United States is now the global industry swing producer, with the majority of growth coming from the tight oil sector. Right, so that's not the only pattern I found. Now we're going to go back to 1970. And that pinpoint is January 1970 to the number 100. So we have a period of stability, and then that happens. What are we looking at? You're looking at the decoupling of the US dollar from the gold standard and the start of the fiat currency experiment. That point there is actually far more influential than actually what happened in 2005. So why do we care about oil? Apparently we're getting rid of it. This is GDP versus oil consumption in terms of total liquids. All nations I could get data for, and it all has an R squared of 0.92. The implications are as follows. More oil, more economic GDP. Less oil, less economic GDP. No exceptions. We are an oil-dominated society even now. So there's the larger European economies, United States, BRICS, and there's the Nordic frontier countries I'm working with at the moment. We're an oil-dominated country. So let's look at oil. We had a localized peak oil in November 2018. Then we had COVID, the gift that keeps on giving. Is it over? Are we about to go again? No one can tell me. Right, yeah. So this is one of Art Berman's charts, by the way. So coming out of COVID, it looks like our production's rising up, and we're about to overrun that record. Let's unpack this though. The blue is crude oil. And then you've got biofuels and natural gas liquids. There is our possible peak oil. Crude oil, it is indeed declining, and it looks like it's not coming back. But we're now getting fuel, especially gasoline, from biofuels and natural gas liquid derived systems. We are forcing gasoline out of the natural gas industry. So we're building in an inefficiency into an industry that's taken decades to get efficient. What this is a marker for we need the after oil plan now, not next week, not in 5-10 years' time. This is not someone else's problem. This is our problem, your problem, actually. So what's the future going to look like? So this is actually a chart put together on promises made. Crude condensate's the dark red down the bottom. It has hit its peak and it never actually goes past that peak. Natural gas liquid derived gasoline expands to the point where it keeps on improving, but 2027 is the projected peak. That's 4 years away, guys. It's going to take 20-30 years to replace the infrastructure around oil once we have the solution. So some of the post-production is not secured yet because money's been promised that hasn't arrived yet. What you're looking at here is the motivation to get off oil and get organized. Right, so how are we doing? What I've done here is put global GDP and oil production on the same graph, and I've pinned them to number 100 and the year 1965 as a starting point. In the beginning, when we were winning, oil was physical activity. Physical activity was economic value was GDP, and so they overlay perfectly. And then that happened. That's when we decoupled from the gold standard and we could just throw money at all problems. Right, so we're separating. Well, how's things now? Well, we've got a ratio of 17:1. So when the fiat currency experiment runs its course, those two curves will have to come back together. And the problems I'm showing today is with the red curve down the bottom, which is the foundation for everything. I'm sure it'll work out fine. So, gas. Now, when I've actually shown this slide before, people who traditionally argue with each other stop whining and start talking to each other. Gas is a problem in Europe because of the Ukraine war. So we are very, very aware of what's going on. So here's some data. The largest producers of gas, according to BP statistics, there's the largest 11. But those producers are also consumers. That's their consumption. So when you actually look at what's their net export to bring to the market, it's actually the green numbers we're after. So let's reorder that table. Now we're actually looking at, well, Russia is producing 234 billion cubic meters of gas a year. Take that away. Europe, who happens to consume more raw materials than anyone else, but doesn't necessarily produce that much, needs 331 billion cubic meters net. Now, if we took Qatar, Norway, and the United States and put them together, that's 322 billion cubic meters, or a shortfall of 9 billion BCM. So Europe is the biggest net consumer, followed by China, but China does all their industrialization. Put China and Europe together, and if we put the next 4 biggest producers together after Russia, United States, Australia, Norway, and Qatar, we still have a shortfall. And that was our net position going into the Ukraine war. The 2022 data has improved things. The United States has ramped up production of gas, and so now those numbers are in a slight surplus. But for them to actually meet that, they would have to give over all existing gas contracts, which is not possible. What this means is Russian gas cannot be replaced from somewhere else in the market, and Europe is now in a conflict with no visible, acceptable outcome. Ouch. There's deep politics going along here. There's a reason for this. We can discuss that later, I believe. What we're looking at, what I'm now seeing, is these 3 things: minerals, money, and energy. They're all interacting. They're actually all part of the same thing. We have one, you have the other 2, right? And this is how we should have been looking at things all along. They cannot be separated. So when we're going forward, we have to think in these terms. So what did I do to actually sort of get at least some discussion going? There's going to come a point when, so this is x-axis is time, and then the y-axis is how many non-fossil fuel systems are coming online. So that we will bring them online as fast as we can. But there'll be a point when the full system is replaced. So the system around us now, all the cars, the trucks, the lighting, the power, it's all non-fossil fuel. And then from that point on, we'll have a more and more conventional growth, or so we'd like to think. The IEA has predicted or declared this is to be done by 2050, 27 years from now. So my report is to model that point there. What would that point look like? So what do fossil fuels do for us now? And well, how much extra electrical capacity has to be developed on the grid? How many cars, trucks, ships, trains, airplanes? How many batteries will be needed? How many new power stations will be needed, and what kind? How many solar panels? How many wind generator turbines? And then the reason for all of this is, what is the quantity of minerals needed to manufacture the first generation of this stuff? That was the mandate I started 5 years ago. Baseline calculation goes like this. If you couldn't be bothered reading the report, fair enough. Okay, 1.4 billion vehicles traveled an estimated 16 trillion kilometers in the calendar year 2018. Now, in 2021, about 1% of the fleet was electric vehicle. The rest of it was ICE. Renewable energy in 2022 accounted for 6.7% of the primary energy pie. The point I'm making here is the non-fossil fuel system has not been constructed. And as it's not been constructed, it can't be recycled. So the idea that the European Commission has that all its raw materials will come from recycling is probably going to prove to be bollocks. So the new tasks are, we now have a fleet of 1.39 billion vehicles. We need to charge those vehicles across the year. That's the power we need. So we need to produce hydrogen as a direct fuel. And now we want to produce steel in a hydrogen atmosphere and not use coal. We now have an ammonia economy. So there's the ammonia we need to produce, some for fertilizer and some for fuel for maritime shipping. And then we need to phase out existing fossil fuel power generation. We're going to heat buildings now, not using gas, but using heat pumps that all require electricity. And that's the butcher's bill. 48,909 terawatt hours of extra capacity over and above what we have now. So we also believe that we're going to have biofuels. Now, the belief is 37% of the maritime shipping industry will be biofuel powered. That's the belief. You know about beliefs and reality, right? So the aviation industry is considered to contract 38%, and then it will be on biofuels. To do this, we need 940 million tonnes of biomass annually. Put this in context, the wheat crop in the same year was 400 million tonnes. It's probably not going to go the way we think. So here are the numbers graphically. On the left is power generation in 2018, 26,652 terawatt hours. Oil, gas, and coal, that's what we want to knock out. The systems down the bottom we're allowed to keep. Hydro, nuclear, wind, solar, geomass to waste. And this is what we're going to bring in. So we want to bring in a new power system substantially larger than the system we've already got, using power systems that are not as effective. So the jobs are as follows: replace fossil fuel power generation, charging electric vehicles, hydrogen production, steel, ammonia, heating of buildings. Right. And so the system will now evolve from 26,000 odd terawatt hours to 58,000 odd terawatt hours, just to stand still with what we have now. So that doesn't account for growth. This is the way the system was in 2018. By 2050, the transport fleet is probably going to be 2, maybe 3 times the size. So these numbers, as large as they are, don't include everything, and they're too small. So the IEA, and this is very brave of them, I'm very glad they did this, made a prediction of 2050 what the energy split was probably going to be, where wind and solar now account for about 76% of the global energy split as the primary energy going forward. So this is the energy split that I put together for this study. I would do things differently, but this is what they think they're going to do, and this is what the European Commission has been telling its staff we're going to do going forward. And then what I did is, well, now that we know how much power we will need to deliver, and we know roughly we need the split between the power systems. So then I went to the Global Energy Observatory and looked at what was actually done in the year of 2018. How many power stations? I looked at about 10,000 power stations and ran some stats. What did they actually deliver? Not what they promised, not what's theoretically possible, what do they actually do? And so I got some metrics around the single average power plant of all of those different power slides. And we're able to get things like, availability. Solar, if you look at that, was actually producing power 11.4% of the time. And the rest of the time, it was not producing power. Wind was at 24.9%. Because they're susceptible to the weather. There's no way around that. So these are the metrics going forward. And this tells us how many power stations we're going to need based on the power they produced. And that's how I got this table. We need 48,909 terawatt hours. Okay. And we have like capacity performance of each individual station. We need 796,210 new average size power plants in addition to what we have now, or an installed power of 29.9 gigawatts. So that's what we need, and that's what we have to do. Put this in context, in 2018, the existing power plant fleet was 46,423. So it's more than 10 times. What that is, if you knock out a single coal-fired power station, how many solar panels do you need to replace that single unit? That's what's going on there. That's the mix. The elephant in the room is power storage. Wind and solar are highly variable. And if we're now going to take 70% of the mix, we can't balance it off something else. It's got to be internally self-sufficient. So, what do we think that's going to be? This is Net Zero America. This is what the United States Congress has actually used. It's a study from Princeton University. And it's actually well done for what it is. So, look at that. A new toy. Right, so what they've actually got here is the solid line, which is that there. That's demand load. That's the amount of power we need. And at a day-to-day basis, that goes up and down. At night, we need less power. During the day, we need more power. And sometimes supply exceeds that line, and sometimes it does not. So what they wish to do is catch and collect that and then release it several days later when demand exceeds supply. And to do that, you need about 5 to 7 hours. Okay, that's fine. Watch this though. You ready? The sun in winter is not as strong as the sun in summer. Yeah. They've completely missed that basic premise. 5 to 7 hours of buffer ain't going to do it. Let's look at that. This is Europe power generation. No nation makes just the amount of power they need. Sometimes it's too much, sometimes it's too little. And we trade. And if we want more power, we buy more power. And if we want more power, we burn more coal, we burn more gas. We can do it anytime, anywhere, for any reason. We are not susceptible to the weather. So all networks are balanced and buffered by other networks, almost always using fossil fuel source power. Now, the wind turbines in Denmark are balanced by power from Germany and Sweden, which are gas, Russian gas actually. We've never had to actually balance or run a renewable power system on its own ever. It's always been able to come from somewhere else. So let's look at that. This is solar radiance in Germany. You might notice in summer we get more solar radiance. So if this now represented 38% of the global energy mix, and it had to be turned into a flat line to deliver the power that we need, everything above that dotted line would have to be caught and stored. And everything below that dotted line would have to be power drawn down from our buffer. So the buffer is the grey stuff. So the power buffer would need to collect excess power over about 6 months, store it for 6 to 7 months, and release it slowly 6 months after that. So that is 28 days. Come back here. That's 28 days. Now I used that for my first set of calculations. Obviously, it's not enough. It was to be a conservative estimate. The screams of pain I got from social media were amusing, but I had to keep a straight face. That's 48 hours. That, ladies and gentlemen, is 6 hours or 5 to 7 hours. That is not going to work. That is a blind spot in our current planning. Here's a case study. Concentrated solar power, Spain, where the sun shines pretty well. Right, so they looked at 2 months, one in summer, one in winter, June, November. So this system is actually just contributes power to the grid. But if it was a standalone, it would be a 670 megawatt system. The dark orange is the power buffer we would need to keep things stable. So for the month of November alone, we would need 16.2 days, just for 1 month, in Spain where the sun shines pretty well. Right, this is a blind spot. Now, wind. Wind is very variable. So UK Parliament did a study on this and they found that power production was so erratic it couldn't be predicted. What didn't help is when they did this study, they got hit with an unseasonal storm, but to be frank, that happens. So here down the bottom is a more sensible and well-behaved metered power for a couple of months for the UK. That line there, let's say the dotted line, that chart was flattened into a flat line. That's the dotted line. The red line is 6 hours of buffer. It's not going to work. So the problem with wind is it's variable and you have these massive swings. And the size of the swings are huge. So here is data for 5 countries overlaid. And you might notice these massive peaks. So those peaks vary up to 48% in this data set. And you have periods of lulls where we're below capacity. Now, the point of this slide is to show that when you are having a peak or a lull in one country, you're actually seeing it in all 5 countries. So you can't use Germany to balance Denmark or Sweden to balance France. Just as if a solar powered system is having trouble, solar radiance, it's probably because it's winter and the entire Northern Hemisphere is having the same problem. We can't balance one up against the other. The United States Department of Energy picked up my work and did an audit. And so they've come back and looked at this, and they found that that they did a power grid that serves 100 million people. So it's a reasonably substantial grid. They found conceptually the work is correct. Wind and solar do indeed underperform for about 6 months of the year. So, and not only the capacity factors are low, but they happen to be low at the worst possible time. Winter is when we want to spend power to heat buildings. And that's when things went sideways. So this is the numbers I collected myself from the Global Solar, the Power Observatory. Solar was producing power 11.4% of the time on a global average, and wind was 24.9. So these assets, when you put them in, will be idle most of the time, and there's nothing we can do about that. Oh, there is engineering to actually try and sort of increase the efficiency of that. I think wind is up to 33%, but they're still idle most of the time. Whereas what we're replacing them, like coal, had a 92% availability. Nuclear is pretty good too now, and so on. So this is the nature of the challenge going ahead. So the stationary power buffer, this is the elephant in the room. I originally had just 28 days and 48 hours, but I've now included 6 hours, which is what everyone in the literature believes they need. They still believe it. 12 weeks is probably the real answer. Now, what happens is when you have a wind lull, okay, you've got to let the grid recover. But then you often get a second wind lull or a third wind lull, like a day or two later. So you actually need 12 weeks of buffer to get through that set. And then you need about the same for solar. So that's probably the most sensible answer. Hydrogen. We think hydrogen, well, hydrogen's been proposed as an answer. So if we were to go by these numbers here, that's the amount of power that we'd need to make the hydrogen. Remembering, for every kilogram of hydrogen, we get 15 kilowatt hours of electricity, but to produce that hydrogen, we're putting in 52 kilowatt hours, a 28% round trip. Now, power systems need about 80% to be tolerable in the current. But okay, let's say we did that. The power grid would have to expand between 27 and 81% in capacity to make that hydrogen as a buffer. It's not going to work. We don't even have the technology to produce such a large amount of hydrogen or store it or transport it. But even if we did, it's not going to work. Right. Pumped hydro is how we actually store power at the moment. Okay. Most of the time, that's 99% pumped hydro. So pumped hydro is you've got your hydro system and you've got like a reservoir uphill, and off peak, you pump the water into there and then you collect the power when it comes down the following day. Okay. The study came to a conclusion there's 530 sites around the world where pumped hydro could be done. I don't believe that. And you might notice in Northern Europe, there's very few sites, so that's not going to help me. And when I started to actually look at the viability of these sites, this hairy civil servant sits me on his knee and gives me the talk that they're never going to rezone such a lot of land area. But let's say we have to do it. There's a gun against our head. We're now going to do it. How much fresh water is that going to tie up? Now remember, most of these sites are away from the coast, so it will be fresh water. Let's take the 28-day buffer, a conservative issue. All right. We need 1,949 cubic kilometres of fresh water, and the global annual freshwater withdrawal in 2018 was, 3,990. And to show this graphically, there's our global freshwater withdrawals where the green is agriculture. And the pink is the amount of extra fresh water we will need on top of that. And the real number is at this end of the chart here. Ouch. And the problem is freshwater withdrawals at an all-time high, because our population's at an all-time high. We're not going to be able to get a 48% increase out of this easily. It's not going to work. So all governments around the world believe their power storage needs will come from a battery bank of some kind. This is the Singapore government. They looked at a whole lot of technologies. They rejected all of them. They said it's batteries of some kind. Mind you, they think they only need 6 hours. There is no technology that goes beyond that. Supercatastrophes were rejected because of the amount of time it takes to store the power. Right, so now we've got the list of stuff we need. This is the number of units around us. We've got electric vehicles and their batteries up there, hydrogen fuel cells. We've got wind turbines, 70% onshore, 30% offshore. Solar panels, and the stationary buffer down the bottom. Stationary buffer is the elephant in the room. That's actually most of the resources going into that. And if we don't meet that, then wind and solar is not viable. And that's 76% of the power grid going forward, which means we've got a problem. Right. So then I get into the second part of the work. How much metal do we need? All right, so we have an idea now of the number of units we need and the amount of power that we need to deliver. So then I've gone and said, well, what market share? And so this is the IEA again, 2040, we've got an estimate of the different kinds of wind turbines and their market share. And then we've got the amount of metal in each wind turbine. Okay, all right. So then we can project one onto the other. This is stationary power storage, 2040 again. So I came up with these splits for the study. So we've got these chemistries, we're looking at LFP, features fairly prominently, but all these other different chemistries and they're rough splits. And we've got the content of what's in each one. I actually got the real numbers from a battery chemistry paper. This chart on itself, this is what the IEA put out, kilograms per vehicle, but a bus will be different to a passenger car. So that, yeah, it shows the point, but that's not what I used. All right. So then we got to this point here where I actually calculated the amount of metal we needed all summed together. This is for 28 days, and there's 48 hours next to it, and I've got all 4 calculations to show you graphically. And it's by metal, aluminium, copper, zinc. Now we're going to get nasty. This is the mining industry in 2019. It's the last year before COVID. It's the last sensible year of data. So this is where we're actually okay. This is the number of years we think we're going to produce to hit that target with the mining industry at the moment. Copper, 254 years. Anything more than 27 years is red. Nickel, 532. Lithium, 13,000. What's happening there is we mine lithium in a very boutique fashion, in a small quantity, but now we want it like steel. Some intellectual midget decided to have a solid state batteries with germanium in it. Now we're mining 143 tons a year, but we need 4 million. So that's 29,000 years of production. Here are the numbers graphically. Production is black. Pink is your 6 hours, all the way up to blue for the 12 weeks. You're looking at the mining industry's ability to deliver. Now remember, this is at the first unit of stuff, and they wear out. Right? They wear out. Your car's going to wear out. And in 25 years, we do it all again. Open more mines. It's easy, right? Okay, right. So we've got this amount of copper and nickel. That's the amount of reserves that we've got. And this is the percentage of the reserves, economic reserves in the ground versus what we've got. So all our, for every 1,000 deposits discovered, 1 or 2 become mines. It takes about 15 to 20 years to build a mine. And for every 10 mines producing, we lose 2 or 3 to market conditions. So let's show these numbers graphically. These are the numbers for mineral reserves. Not enough if we need to hit the blue. That's a log scale. And they say, well, obviously we're going to go to resources, right? Reserves plus resources. Still not going to hit the blue. Now, one of the most flamboyantly stupid ideas I've heard in a long time is we're going to mine the sea floor. And the Chinese are already doing it. So all right, mineral reserves plus resources plus undersea resources, still not enough. Right, and here's the same numbers shown in a linear scale. It's a dumb idea, guys. This is a crap plan. We really need to build a better one. So when the fail is so bad, you need to double face palm. That's the situation we find ourselves in. So all these units that replace a fossil fuels technology system in some form. Now, the wind is renewable. The wind turbine is not. It wears out after 20 years or 10 years in some cases. You then got to take it down and replace it. So the renewable systems are actually replaceable. Each one's manufactured from metals, and as it's not constructed yet, it can't be recycled. So this is a mining story. Minerals are the new oil, but which ones? If the environmental movement does not join hands with the mining industry, we don't get our green transition. Simple as that. So we're coming to the end. Let's talk about copper. From 2020 to 4000 BC, the human species mined 700 million tons of copper. To keep up with economic demand, we will do the same thing in the next 22 years. Reserves are about 880 million tons, so we've got 30 years of production ahead of us. Yes, there's a pipeline of more deposits coming online, but it's not big enough for that. What we don't have in here is the 6.1 billion, with a B, tons of copper, just to manufacture the first generation of renewable technology around us, which is 8.8 times the historical quantity. It's a bullshit plan, it's not going to work. What does it mean? After oil, plan's not good enough. We've seriously underestimated the task. We will use battery chemistries other than lithium ion, that's not rocket science. Energy return on energy invested for renewables, they may not be strong enough to replace fossil fuels in their current form. Hopes for a future technology breakthrough to somehow magic up more commodities does not honour the resources we have left, and the current ecosystem has no concept of its dependency on minerals. So what's happening is the limits to growth study. 2 minutes, we're good? Yeah, all right. What's happening is this. In 1972, the Club of Rome released the Limits to Growth report, and they came up with this model. Resources decline, but they decline to a certain point, and all other systems will peak and decline as a consequence of that. They were bagged mercilessly. But a friend of mine, Graham Turner, in 2008, put 30 years of data on top of their model from 1970 to the year 2000. We are following the standard run, and that's the standard run. So this conceptually is a good model for what's happening to us. What this study suggests, we're not going to do this for the entire human population. All 8 billion people. Most people won't look at this anyway. We don't have enough time, we don't have enough money, and we don't have enough raw materials in the ground. So what will probably happen is a significant reduction in societal demand, which implies a radically different system of governance. Now, the whole green transition, to me, is a stepping stone to something else. We should probably consider what that something else is. Ecological reality and biophysical limitations assert themselves. And the environmental movement and the industrial system will both evolve into something else we haven't seen before. The whole system needs to evolve. Now, so far there's been way too much talky, not enough wickety-whack. Thanks. All right, questions?
We have plenty of time for questions.
So tomorrow I'm going to talk about the solution set. You know, there's been a few screams of pain when I've presented this to various, and they all always ask, fix it. Ah, yes.
Yeah, so I forget what fraction electric heat or something. So what you charge daytime, basically that for that particular system, or fraction.
What system's that?
Basically, it's self-buffering because you charge daytime solar bill.
What system are you referring to? What system are you referring to?
Just the electrical vehicles.
Okay, yeah.
Not the whole
Yeah.
48 days.
Okay.
Isn't it that system at least self-buffering?
How so?
If you schedule charging.
Ah, now I see what you mean. Right. So there's 65 terawatt hours of battery capacity that needs to be charged. Right? And if you do charge off peak, right, the system, there's too many batteries that can actually charge off peak. You can charge some of them, but you won't be able to charge all of them.
Well, you can capture that midday.
So you need a battery capacity to do that. You need your power buffer to do that. I understand what you're saying there, as in you take the excess power during the day, right, and then you actually charge during the night, right? But the whole rest of the system is going to consume that buffer, right? So, yeah. So the EV systems are the solution, in my opinion, using a different battery set, but it's got to be separated from the entire rest of the system. We're going to break the system up as the solution.
Right, so
Yep.
there are other subsystems, some applications that require high temperature.
So here's where the trouble starts. Conceptually, there are other systems, but the numbers behind those other systems simply haven't been done. We haven't done the maths to the point where we can actually put them into a study like this, right? So conceptually, there are a whole lot of solutions on the ground. We're not doing our homework on all of those systems. The proposal of having the EV system charging at night works for a small EV system. When you've got a large EV system, we run out of capacity very quickly. And that's where we actually need to get the numbers. How much power do we actually need? How many EVs do we need to run? How many kilometers do we need to, or miles do we need to actually look at? And so that's what needs to be balanced up. The answer is we just use less miles, right? And the answer is we go more communal transport. Then such a solution might be viable. So, yeah.
So where does recycling fit into the equation?
Right, that's an interesting question. So I'm part of the recycling world at the moment. The metals that we want for the green transition are comparatively exotic. Yes, we mine lithium at the moment and cobalt and everything, but the quantities of metals that we now require don't exist in the current situation, in the current system. It's just not there. We can recycle this metal if we get the right residues into the right process plant. Problem with recycling is not technology, it's society's ability to collect the right wastes and put them into the right streams and get them up to the right plants in enough quantity, because each recycling process plant is optimized to one or two metals in a given waste stream, like phones or batteries or white goods or whatever. So recycling is in there, but we're not geared for it at the moment. And the whole system has yet to be constructed, so the actual volumes of these exotic metals don't exist yet, so they must be mined. So recycling is in there, but that's the next generation.
Do I, excuse me, do I understand correctly that something as non-exotic as copper is still a factor of 10
Yep,
beyond our capabilities to have in our hands?
yep. So watch this. Anything electrical has copper in it. At the moment, we've got a vast number of fossil fuel units that we want to replace with something electrical. Now, copper is the rate determining step for everything. Yes, copper is where we depend on it now, but the size of the task in front of us is driven by the number of units. Like each wind turbine, for example, has a cable as thick as your leg made of pure copper to connect it to the power grid. An offshore wind turbine has a long cable, right? So, and we're talking about millions of them. So yes, something as basic as copper is about to become as valuable as gold. And in fact, copper will become the rate determining metal for the next human industrial system. Ouch. Yeah.
Maybe this is a fair question, but
Oh, I like it.
by 2050, and how big do you think the total energy economy of the world will be relative to today? And what fraction do you think will be electricity then, as opposed to the
So
10, 15% now?
I'll show you what the IEA believes. Okay, here. The IEA has predicted that by 2050, the electrical power grid will be 71,200 terawatt hours. Whereas all my numbers are based on 2018, so 26,000 to 7,100. So they're talking about like a factor of 2 or 3. And so the transport system, because everything's geared to growth at the moment, we must grow, we must have profit. So the transport, our population's growing, and we must have economic growth each year. So the transport grid will be 2 to 3 times the size, and the electric power grid will be 2 to 3 times the size of what it is now. And all these numbers are to replace what we have now. So these numbers will telescope up. What the real number is, I don't think anyone knows, because that work hasn't really been done. Substantially more than what we got now, unless something really strange happens that's unprecedented, that somehow we start consuming resources like we do, and somehow we don't need power and energy like we do now.
Thank you. So this morning on The Economist, they announced that 35 million tons of green metal will be needed by 2050 to sustain current activities. Now, I wondered what your opinion on that number was and what green metal is.
So this touches on something that's actually a little upsetting for everyone who's looking at this. The IEA, World Bank, IMF, United Nations, all of those guys, they're bullshitting, right? They are making numbers and assumptions that are not supported. They don't tell you how they got that number. What I've tried to do is show where I got my numbers from the bottom up. They don't do anything like that. They don't do any estimates of how big the transport fleet is, or how much power will be needed, or how many of them will be solar panels, none of that. What I believe is all of those organizations are releasing information to try and placate the public, that the situation is not necessarily as bad as we think. You don't need to panic just yet. What they are being forced to do is revise those calculations. What they call a green mineral, and this is also another dodgy thing they do, is anything involved to actually do the green transition. So copper, nickel, cobalt, graphite, rare earths. But when you actually look at it and you actually sort of, well, if we were to look at the solution set properly and really had a frank conversation, how much of this stuff do we actually need? And can we actually simplify things? And can we actually use innovative ideas? The answer is yes, but not while having economic growth and increased complexity. So the business model behind what the people who control our society at the moment are the managers of the hedge funds, capital. They're international. What do they think? They want more growth, more complexity until it all crashes, and they'll make money out of that as well. They don't care about us. So we've got to break free of that thinking and do some proper problem solving. And it has to be radically different. And there are solution vectors out of this, by the way.
Just looking at that chart, there's a strong assumption that nuclear is not going to increase. Maybe there are good reasons why we don't want that to happen. But when society is facing this sort of tipping point, I don't know, maybe it's a social question, could that capacity expand?
So I did
Or
a
could
study. Yes and no. So I did a study with asking the question, could the nuclear fleet expand to be useful? Right, and if we actually reduced the build time for a nuclear power plant of average size down to 5 years instead of the 25 that we now use, but 5 years, and we brought on a net new 25 new power stations every year, starting 2025 onwards. The question was, how much extra electrical power can be brought to the grid? And we just kept going. Now we want to actually increase nuclear so it becomes the primary energy source, and it's now got to supply all the charging of batteries, making hydrogen, all that. So the answer was, you get out to 75 years, year 2100. We've now used all existing nuclear resources, reserves. Yes, you can go and find more, but that's just the numbers I had numbers for. But in 75 years, we get 60% of the way there. So if we need to be operational and we need it to be most of the way there by, say, 2030, and conventional nuclear can't expand fast enough. Now, I did a study, this was actually what the IEA believed. I did a study, what would happen if the nuclear cut went to 30%? And yes, things substantially reduce in terms of raw materials. So less solar panels and wind turbines are very, very intensive in their material requirements, and you don't need the buffer to go with them. So yes, it would work, but could the nuclear industry expand so quickly, so fast? No. But what I will present tomorrow is an evolution of nuclear into something else that might work, that has a different footprint. And like I said, one system has to evolve on one front. What is that? And if we were to think differently and do things differently, could something come of that? So the idea is to actually assemble about 20 or 30 unorthodox ideas together and actually look at things and do things differently and change how society operates. Then we might get somewhere. So the answer is yes and no, no and yes.
In Florida, we have a lot of sunshine.
Yep.
So I've been thinking about solar power a lot and thinking about our earlier conversation about developing localized energy systems and communities. So one size isn't going to fit all, and I think that's definitely part of your message. And that got me thinking about some things I've seen in the news lately about new technologies that utilize the sun to create energy, including different paints that are used on car roofs, surfaces for roads, right, that utilize solar power and convert that to energy. And I wondered what your thoughts were on some of those new technologies, because I am kind of a doubting Thomas. And the first thing I think of is, oh my gosh, what are those things made of? And aren't they just going to create another hole in the earth somewhere?
Right. So new technologies coming online, yes, they're useful and they will achieve something. Will we be able to manufacture them in enough numbers to be useful? That remains to be a question. I don't think they will arrive in time in large enough numbers to move the needle. What will probably happen is if we change our demand side of the equation, where we can actually sort of have a power source that is highly variable. If we can do that, then all that stuff's great. Now, in terms of what is a long-term solution, the sun obviously is the primary energy source in the solar system. More energy comes from the sun from anywhere else. But the technology of accessing power at the moment is photovoltaic. It's a primitive as hell system. I'm a physicist first before anything else. So my feelings and thoughts on this are we should be looking at the sun and the energy from the sun in context of can we access that power some other way? What I mean is I like some of Nikola Tesla's ideas where everything is frequency and vibration. Can we access energy directly that way from the sun? And so what I was talking about is a technological paradigm that doesn't exist yet that will leapfrog everything. That's the sort of thing I'd be reaching for. And of course, when you start talking like that, capital investment groups run screaming from the building. Yeah. So, yeah.
Question from Olga on Zoom. How about nuclear fusion that is expected to become commercial in the 2030s?
Right. So if someone can get nuclear fusion going, our worries are over. I have two problems with fusion. One, it always seems to be 10 years away, and the goalposts keep shifting. So the technical problems they've got to solve associated with fusion are enormous. And two, the system where they've actually got like a fusion reaction that actually was stable, the amount of power they pumped into this thing was enormous, right? So we've got in a small area, enormous amount of power. So when something goes wrong, it's going to go really wrong. What I see is all fusion systems at the moment are a stepping stone at best to something else. We don't know what that something else is. Once someone gets it going though, great. I can get another job. I can retire. That'll be great. But we are looking at the deterioration of existing systems happening now around us. And the next 10 years will decide how things will go for humanity for the next 100 years. So we need a solution on the ground in the next 3 or 4 years to be operational. I'm a fan of fusion, but it's not going to arrive in time.
So for those of us who can't come to your solutions talk tomorrow, it sounds like you foresee sort of a reduction in our energy use is inevitable. So if you could place us historically backwards to where we would end up, what era would you?
So we've got several moving parts happening at the same time. First, we've got to contract our system from a just-in-time supply grid across 6 continents into 1 city. And there's technology to do that, but we've got to do it. Then we've got to scale back our requirements for the future. Like, what do we think we need? simplify it or be simplified. Right, so if we can simplify that, and if we can design things to be recycled, then we can recycle, whereas at the moment we won't. Right, so then you've got the idea of, well, technology complexity, if it does simplify down. I would envision, for example, say an 1880s level of complexity, but using modern technological equivalents. Right, so we still have the technology we have, like computers and phones and cars, but the complexity the society will have is what we saw in the 1880s. And it will not be even. There'll be areas of low technology and areas of high technology around industrial systems of various kinds. Like the simple thing of how do we make a hospital self-sufficient is more complicated than you might think. A single hospital, what's the footprint of that? If we have to collapse that down, what would that hospital look like? And it also depends on, are we successful on bringing online alternative energy systems that are dense? Like oil is a calorifically very dense oil source, energy source. Can we replace that? If the answer is no, then we must simplify further again. So it's contingent on things that haven't happened yet, and it requires people to cooperate together when we'd rather pick fights with each other. So how long's a piece of string? I actually believe it is possible, and it will happen in some parts of the world, but not others.
So I'm just curious about the mining industry. What is the reason why the collection has been so set back?
Mining or recycling? The collection? What do you mean by the collection?
Collection of the minerals.
Ah, right, okay. So for the last 30 odd years, 40 years, there's been data patterns on the ground. We've mined out all the high-grade deposits, all the really good stuff. There's a small but high-grade deposits, and now we're left with the massive low-grade deposits with hard rock and the fine mineral grains that we've ground down. Costs have gone up. The mining industry is struggling with rising costs. More energy is required. Operations have to be bigger to survive. There's more consumption of potable water. It's all going in one direction, where it's getting harder and harder to deliver on targets. And they've used economies of scale to keep up with demand. Right? There will come a point when that will become difficult. A lot of the metals that we've required for technology too for the last century have been around internal combustion engine supported technology. Take that away, and now we're going to have a sort of substitute technology that's going to be electrical based. Everything moves, everything changes, and they're moving into metals that we've only mined in relatively small components, or they're trace elements. They're what's called carrier elements. When we want indium, we're really mining zinc, and the indium is a trace element in the concentrate. If we don't mine the zinc, we don't get the indium. That's the simple answer for that one. It's a more complex version.
Other questions? Let's give Dr. Michaux a hand. Tomorrow at 30 at the Rights Union in the auditorium. We will hear the solutions to these.
Some of them.
Some of the solutions.
Everyone said this is a depressing talk. Could you please stop that? Right? And the Swedish government said, all right, smart guy, you scared us. Now you're going to fix it. Right? And so a series of solutions have been put together, right? But it requires that we think differently and we evolve and we actually step up and do it. But the hardest thing is the way we think as a paradigm and as a social contract has to shift. So tomorrow, I'm going to present some solutions, but they deeply offend the existing system, thus the title. Right.